All right. Hi, everyone. My name is Berwout of Robles. I was speaking to you about HTTP2 and server-sent events and reactive streams. We're going to start with a little bit of HTTP history. How do we get to where we are right now? And what challenges did we face that led to the development of HTTP2? We're going to see how we solved them in the past and how we could solve them in the future with reactive streams. I'm going to give you a small demo on how to use reactive streams in your Spring Boot applications. And finally, we're going to finish off with a musical piece, which will be played on your phones in the crowd. And all of this has something to do with an orchestra, but more on that later. A little bit about me. I'm a little bit adventurous. I like to do a lot of sports, and these are some of my hobbies. I work for InfoSupport, which delivers software consultants. And I work for the Professional Development Center. Well, that's quite a mouthful. We build software for software developers. And I get to look at new technologies and see how we can use them in the field, which this is a small part of. I said we're going to start with a brief history of HTTP. How did we get here? We started in 1990, 91, and it was a one-line protocol. All you had to do was send one line to a server and receive a response. It was HTML only, and it was request response, which means you would send a request to the server, it would receive it, it would send you a response, and then you would terminate the connection. It looked something like this. You would send a response, send a request, sorry, and receive a response. Very simple. If only it were still that simple today. On to HTTP 1.0. We realized HTML might not be the only thing we want to send. So the first browsers came along about 1994, but HTTP 1.0 started way before that. So what did we do before that? We used command line interfaces to send requests and receive responses. It had many differing implementations, and there was not one HTTP 1.0. But around 1996, the HTTP working group published a document which detailed the common usages of the HTTP 1.0 protocol. So this was not a formal standard. It was just like, most of the people around the world are doing this, and you should probably also be doing this in your browsers. But it wasn't anything formal. Some features of note in HTTP 1.0, why they were so important. We had request and response headers. We could finally tell the server what browser we were using, where we were connecting from, all relevant information. We had a response status for the first time. So 0.9 had nothing to indicate what happened to your request, which was kind of awful. And we had content types, which led to the creation of the internet, because we could send pictures, which is awesome. What did that request look like? Most of you will recognize this probably. You had an HTTP verb, which indicates what you want to do. You have a resource identifier, which tells you what you're going to get. And then you had a version for the first time, because yeah, we had two versions, although 0.9 was never fully official. And we had headers, so it was no longer a one-line protocol. We needed these headers. And then there was a blank line to separate and any request data you would like to send. The response looked fairly similar. We had a status line for the first time, 200, okay, our request succeeded. Nice. Some headers, a blank line, and any data we would send. So the same data, but this time in an HTTP1 request. HTTP 1.1 came along. They started working on it about 1995. It was published in 1997, sorry, and it was the first formal standard. So they actually said, this is what we define as HTTP 1.1, and you should follow this for the first time, which was a lot better because now browsers responded in sort of the same way to your web application. Some features of note. We had keep alive. Before, we would send a request, receive a response, and then terminate the connection. And every time we would have to initiate a new TCP handshake for every request. So they made keep alive, which is default. You don't need to send a header for keep alive. It keeps your request alive for 30 seconds by default. And they also backported this into HTTP 1.0 because they thought it was such a good idea. We had chunked encoding, which basically TCP layer also already divides your packets into smaller chunks and sends it to you, but then assembles it before it sends it back up to your application layer. And now in the application layer, you had the option to receive chunked packets, which basically means it would chop your request up into chunks, and then every chunk would be delivered to your application. So if you've ever seen an image, like way back, when you open a web page and it would start loading line before line, before line, before line, that was chunked encoding doing that for you, which was a very nice feature to have because otherwise the user would have to sit there and wait for 50 seconds for the damn image to load. We had cookies for the first time, which is a way to store state. We could like log on and store stuff about our user. What did he click on? What's interesting for him? Which is a very important feature. A bit less important lately because of the cookie laws in our countries that are making cookies somewhat annoying to use. We're still using 1.1 right now. Most of the people are. About 28% of the web already uses HTTP 2.0, but we still got a long way to go. So HTTP 1.1 is still full in use. But what's the problem with HTTP 1.1? Why didn't we keep using 1.1? We had a few problems. One of them was we had an extreme growth in connected devices. Your phones now also connect to the internet, but also your fridge, your microwave. Basically, everything connects to the internet. And smaller processors connect to the internet than before. Before, we'd only be your computer or server. There was a huge issue with responsiveness. When Google and Facebook started getting down to 200 microseconds, 300 microseconds, users would expect nothing less of you. And if your page took 3 seconds to load, they would just not load your page. So there was a huge rush for responsiveness. It didn't have any support for very high volumes of data. And it didn't have any support for the server to send you any data on its own without a request. It was always request response. We had some solutions for the responsiveness problem. One of them was polling. We would just ask the server, please send us your data, 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 and keep going on every second, which is very annoying for you and for servers. We had long polling, which was a little bit better. We would ask the server, please send us data when you're ready to send us some data, and then we'd wait and sit there, and then the request would time out if they'd sent nothing, and then we'd open the request again. So we'd open less requests, but a big problem with long polling was that we'd keep the HTTP connection open for 30 seconds, and we only had a limited number of HTTP connections. So the more you long poll, the more you block your other requests, basically, and you could end up in a state where you basically could not do any HTTP connections. Then we developed WebSockets, which is sort of a solution, but it's actually just poking a hole in the HTTP protocol and saying to the server, okay, we're going to talk binary from now on. And it was bidirectional for the first time, which was very nice, but you'd have to make your own protocol. There was nothing predefined. Right now, there are huge libraries for WebSockets, so it's still a good option to use. But application firewalls and middleware don't deal with WebSockets all that well because they don't know what's going on in there. It's just a binary stream. Then we got server sent events, which was an idea formed in HTML5, which was basically it used chunked encoding to send multiple datas over a single request. So you would open a request like you would at long polling to say, send me any data when you have any, and then we'd use the chunked encoding to send tiny bits of data. It wasn't what chunked encoding was meant for. Chunked encoding was meant for large files like images, but we abused it for server sent events, and it worked. It worked all right, but it had the same drawback that long polling had, which was that you'd have to keep your HTTP connection open at all times. So development on HTTP2 started about 2012 when Google realized we can't handle this load with HTTP 1.1. We can't handle all these devices connecting to us, and we can't be responsive enough. So they started with a project called Speedy, and basically the HTTP working group said, we're going to copy that, and take a direct copy and have Facebook review it, and then make it into HTTP2. So it's a direct copy of Speedy, basically. For the first time, it was a binary protocol, which is much better for the smaller devices we also put on our networks. And it was published in 2015, so not so long ago. Some features of note. For the first time, it was bidirectional. The server had options to push stuff to the client without the client requesting it, but more on that later, because it has a little bit of a side effect. It had header compression. The guys at the HTTP working group and Google realized that most of the time, when we send requests and receive responses between the users, a lot of the headers we use are the same for every request. So it'd be a shame not to compress those. And because it was a binary format, we had the ability to do so. So they basically recognize which headers are getting sent the most, and they compress them down to the smallest format, which is very nice. We had server push, which is the bidirectional aspect, basically. But server push does not send data to your application. It sends data to your browser. And then your application still has to request it, but your browser already has it in cache, which is very nice, because it's close by. And then the best feature, we had multiplexing. Like TCP, multiplexing is when you divide your request up into bits and send them over a single TCP connection, and on the other end, you just split them back up and mash them together again and get your request back. And this means that when you send multiple requests over a single HTTP connection, you can now do that. You don't have to open multiple HTTP connections anymore. So you just need one. And HTTP2 only uses one HTTP connection, which for servers is very nice. Then that was all cool. How do we use HTTP2? Because I just said only 28% of users are using HTTP2 right now. The best part is you don't actually have to do anything as a software developer. It's implemented in your web servers and your browsers, and your web applications don't even need to change. There's one but. You do need to use SSL, but it's 2018, so everybody should be using SSL. It's implemented in all major browsers and web servers by now, and if it's not implemented in yours, then it's not a major browser or web server. Then about server push. Server push, like I said, pushes data from the server to a browser cache. So actually what's going on is when you request an HTML page, usually embedded in that HTML page is a JavaScript file and a CSS file. And you're going to need those. But in the old situation, we would only know we need those when we receive the HTML page, because then we'd read, oh, we need to get this JavaScript file as well. But now your web server can say, oh, you're requesting that HTML file. You're probably also going to need this. And it pushes it over the same connection. And it lands in your browser cache. So it doesn't go to your application directly, but when your application receives the HTML page, it goes looking for the JavaScript file, and it's like, oh, I already got that right here. And it's very nice. So in a picture, you're using a link header to define which files you want to send, and it has the rel preload, which is how you can recognize it. In a picture, it looks something like this. So you're going to request the HTML, get the HTML back, and then request the CSS, which is not nice. And in the new situation, you're just going to get the CSS, and you can just get it from your browser cache. HTTP2 meant a new life for server-sent events, because like I said, it was kind of nice that we had server-sent events, but you'd have to use up the whole HTTP connection. And because HTTP2 uses multiplexing, we can now make that much easier. We only need one HTTP connection to do multiple server-sent event streams. And there's no head-of-line blocking. And head-of-line blocking means when you're waiting for a long request to finish. Because we're no longer limited to 6 connections. Then a little bit about why you would use WebSockets versus reactive streams. The middleware support is much better for reactive streams. your applications almost always understand HTTP2, and they don't understand binary streams. Large amounts of bidirectional data still require you to use WebSockets, sort of, because every request you send over an HTTP2 stream does still need headers, and you have to make those, and it costs a little bit of performance. So if you have a large amount of bidirectional data, you might want to still want to use WebSockets. If the client is sending as much as the server, then you might still want to use WebSockets for the same reason. The client sends a lot, you have to make a lot of requests, and it costs you processor time. If it needs to be really, really, really real time, you might still want to use WebSockets, because like I said, HTTP2 has a little bit of extra overhead. You have to use an SSL connection. And it might get caught up in your application level scanning. If you have a lot of developer support for WebSockets and all your developers know how WebSockets work and you have libraries written for WebSockets, there's not really a reason to go into reactive streams for you right now. On the other hand, if you don't have all that, you're still fine to go into reactive streams, and it will be almost real time. And I will show you how real time it is in just a few minutes. The concept server sent events became what we call reactive streams, because we now have these streams of data that we can use over a single HTTP2 connection. When you go reading for reactive streams, this is sort of the terminology you would get. It's responsive, it's resilient, it's composable. It all sounds very fancy, but it doesn't really tell me a whole lot as a developer. So I was like, this sounds very cool, but what does it actually mean? Then I went looking for the main goal of reactive streams, and it says to govern the exchange of stream data across an asynchronous boundary, which still doesn't tell me a whole lot. It's very abstract. So I went, how can I make this into a real-world example people will understand? And I figured I need a real-world thing that I can use as a metaphor. And that's where the orchestra comes in. And this is actually an orchestra I sometimes listen to, because my mom is in a choir, she sings, and they do the background music, so it's kind of cool. I'm going to try and see how these terms we just saw fit on this orchestra and what that means. So it's composable, like music. Music is very composable, so it fits it immediately. You have a form of flow control. The director will be waving his stick, and the band members will be reading their sheet music. It's message-driven, in this case music-driven, close enough. It's resilient. If one of your orchestra members dies, I hope he doesn't. But if he does, the music still sounds all right. And if some more of them stop playing, it still sounds all right. If half of them are gone, it's going to be a little bit of a problem. But it's responsive. What that means is when the director waves his stick, the orchestra has to respond. They do so in their own time, but they do so very fast, because otherwise the music would sound very badly. It's elastic. The best example of elastic, which I like, is that there are two contrabasses over there, and the guy on the right plays very statically. He plays a little bit like this. And the guy on the left is really, really ecstatic. He plays like this. Which is, I just love to see the contrast between them two, the two. But what elastic means is it doesn't matter if you put a lot of data or a small amount of data or large chunks of data or small chunks of data through the reactive streams, it's going to keep working. So it doesn't matter how you perform, it's gonna work for you. Then it's asynchronous. Like I said, the band members and the director have to, in their own time, decide what to do and when to do it. And lastly, this one is a little bit hard to explain in terms of an orchestra. It's back pressure. It would be something like the audience leaving. It means you're sending too much, I can't take it, please dial it down a little bit. So I guess the director does have a way of doing that, because he can slow down. Then applied to reactive streams and a little bit simplified. So there are publishers in reactive streams, which is the musicians. There are subscribers, which is the listeners in the audience. There's asynchronous streams in the middle, which is the coming together of music, basically. And reactive streams is a collection of interfaces that helps us manage that. So in theory, they are the music sheets combined with the director waving a stick at the front. And then something funny, I didn't make this picture, but they used volume to define back pressure, which I kind of like, because I applied it to music. Then how do we use this concept of reactive streams? What I'm going to show you is Spring 5 and Reactor, but we have a bunch more libraries we can use nowadays. In Reactor, there are a couple concepts you need to know about. The first one is a Flux, which is a publisher. So it makes music. Then we have a Mono, which is also a publisher, but it's a very strange kind of publisher. It's like the guy in the back that hits the gong loudly once and then stops for the entire performance. So it's a publisher that only sends one event and then it stops. We have a processor, which is kind of an in-between block, which can do both. It can receive events from a Flux and it can publish it on the other end. It's used to do stream manipulation, basically. And we have a subscriber, which in Flux terms is usually a core subscriber, but it has the subscriber interface. Then a small demo about how we could use this. In this demo, there is a security leak, so don't use this demo in production whatsoever. It's just to show you how easy it can be to get started with reactive streams. Hang on. It's not working. There we go. All right, so this is my Spring Boot application. Who here has seen Spring Boot before? All right, so everybody basically knows this is my controller. It has a GET request. It produces a media type text event stream value, which is your event stream. Here we see the return type of my method is a Flux, so it gives me a publisher. And Flux has a nice factory method, which is called just, which creates a Flux from the values listed behind it. And it has some nice methods to let us delay time between sending events. Then how you would use this in JavaScript is actually very simple. You have an event source. It will do the GET request towards the URL you define there. And then when a message comes in, we publish it. And on an error, we just close the event source. So very simple. And my publishing function, this is where the security flaw is. I'm using the inner text. I'm manipulating the inner text of my HTML document, which you should probably never do. Let's run it and see what happens. There we go. So we're expecting to see the values pop up one at a time and 1 second delay between them, like we've seen. All right, that's nice. But I kind of want to use this to see if I can make the real-world example of an orchestra into an application and see if we can build the real-world example. So how would we go about doing that? Well, first of all, I would have to send notes through my stream. So let's get started on that. Just enable this one. So I have a second Flux right here, which I just enabled. And it's just as simple as the first one, actually. I'm still using the delay to measure time between the notes I send. And right there are the notes I'm going to send. Does anyone recognize this song by any chance? It's House of the Rising Sun. And down here, we have a new method, the flux concat, which is one of the composability features we have. We can combine multiple fluxes into one flux. We can do it in a lot of ways, but this one just sticks them all behind each other. So let's run this one, see what happens. All right, so here we see our notes appearing one at a time. So if I had sound files on my laptop right now, and I would play them when the notes are received, I can make music, right? But if I want to use that to simulate an orchestra, I would have to have multiple people listening at the same time. So let me open a new one, see what happens. And open this one. Oh, but this is kind of a problem, because I kind of want my orchestra to be playing at the same time. It would be bad if they would just start playing notes randomly through each other. So what we see here is the difference between what we call a hot and a cold stream, where a cold stream will always send you all the values it has. And so when you subscribe to a cold stream, it will send you all the values starting with the entire history. And we can't use it to send real-time events at the same time. But if we use a hot stream and plug in on that, we can actually send events to our users and have them receive it at the same time and not receive the history, which is what we want in an orchestra. So how we go about that is slightly more complicated, but it's still fairly straightforward. I have a third flux right here. You see, I also have a stream service. The stream service is nothing more than a list, which keeps track of all the subscribers on my stream. Here we have the processor thing, the middle block I was talking about. So it actually, by calling publish on it, it actually becomes a flux as well. So the return type of this function is still flux. And when we create the processor, when the user subscribes to us, we actually add it to the list. And then when we send an event, we just publish it to the entire list using an onNext function, which is kind of like how the observer pattern would be implemented. It looks very much like the observer pattern. And here we have a publish method, which is also where the security flaw is. If you want to cross-site script me, here you would publish whatever you need. Let me just run this one. Right here. So now what we expect is basically we start with nothing, and then a subscriber subscribes to our event stream, and when we publish a value, it appears for all the subscribers at the same time, which is what we want, and we don't get the entire history anymore. There we go. There's nothing, which is exactly what we expected. And on the other side, and now we can use the publish function to publish whatever note we want. So if I publish an E, it arrives on both the streams. And if I publish an A minor, it arrives on both the streams as well. And if we open a new stream, nothing shows up, and we can start publishing new notes. And they arrive at the same time. So now we can make music, right? So that's exactly what we'll do. I have a website published, and I would like you to take out your phones and follow these instructions. Your sound does need to be on for this to make music, by the way. I've always wondered, if you ask 100 people in a room to turn up their sound on their cell phone, how many of them will receive calls? Let me open the room with you. Oh yeah, if your phone plays all the sounds, you have an iPhone. Congratulations. It also works less good on iPhones. I think they're bad orchestra players, but we'll see. I see quite a few of you are already in here. Let me start by playing a test note. There we go. All right, are you ready? No? All right, let me wait a bit. No. Oh, you can switch to 4G if you want. That's probably much better. Yeah, I do at least. I'm on the hotspot, and 4G is much better for this application. If you're on Wi-Fi, you might sound like an iPhone. So you hear it's not exactly perfect, but to get an entire room to play together, it's quite close to real time actually. And let me try another song. That's kind of nice. If someone wants to sing, they're welcome to. Um, all right, I'd like to try one more, but I haven't really tried this one yet, and it's a little bit more classical, and I'm pretty sure it's harder on the phones, but we'll see what happens. I think you hear a difference between the guys who are on Wi-Fi and the guys who are on 4G. Thank you. But I have one more, which is also cool to show on Reactive Streams. Basically, whoa, someone is still playing. That's kind of weird. Basically, the cool thing about Reactive Streams is that because I have every subscriber I want, I can give you different roles. So if you look on the screen of your phone, you are assigned either bass or treble, and that means I've assigned the lower or the higher half of the keyboard to you, and you can basically send events to specific roles, which is very nice. So I want to try and do this. It means I'm splitting the orchestra in half, so it will probably sound a lot worse. But now you're really making music together as an orchestra, which is nice. Very bad orchestra, yes. In reality, if you would want to make this right, you would probably need WebSockets. But what I wanted to show is that reactive streams are pretty close to real time. And a lot of people still think that it doesn't get this close, but you need to be within 200 or 300 milliseconds to make it sound this good, which is still pretty awful, granted. But it goes to show that it is pretty reactive. And for most use cases, that's fine. If you're not building games that are sending millions of events per second and need to be exactly real time, this is fine. And your firewall is going to be very happy about this, basically. Then finally, I have some extra tips if I can get my screen back on the beamer. There we go. So there are a few pitfalls you can get into with reactive streams, and I want to warn you about those. Naming is very hard, especially in Spring Reactor, I've found, because you're dealing with things called fluxes and monos and processors and unicast processors and multicast processors and core subscribers, it's all very abstract terminology. And once you start using the composability features to combine them together, you're going to have to make objects that combine 4 fluxes in a very specific way. And what are you going to name that? Because it's so far from reality. So naming is very hard. Be careful. Error handling on disconnects is something that is a little bit weird. With reactive streams, you're not going to notice a user leaves by the front end if he doesn't send you that he's leaving. And the first time you're going to notice is when you send them a new event. But if your reactive stream doesn't send them events all the time, you're not going to notice he left. So the room on your cell phone uses what's called a heartbeat. Basically, I send you a pulse. I send you an event every second to see if you respond. And if you do, you're good to stay in the room. And if you don't, I kick you out, which is a way to solve that problem. Like I said, if you're going to combine those fluxes and then do some other transformations and then combine them again and then do some transformations and combine them again, it becomes complexity very fast. So you need to be careful with how you structure your reactive streams in a way that you're still going to be able to understand years from now. I said HTTP2 uses one connection, and therefore you can open as many streams as you want. As of now, the JavaScript implementation event source only lets you open 6, because it still thinks you're on HTTP 1.1, which is not very nice. So be careful with how many streams you open. The nice thing about reactive streams and opening as many as you want is that you don't have to create a whole new protocol. You can update single values at a time. So with WebSockets, you would have to send all the data related to a single page through that socket and make your own protocol on how to handle the page. With reactive streams, you don't have to do that, but you do because you can't open more than 6 right now, which is annoying. Then a little bit about the application. I started playing music. I thought it was a very cool idea, and I programmed my own first song, and it was Brother Jacob, and we heard nothing else for the rest of the weekend, which was a very terrible weekend. So we found out we had to play some different music. Thankfully, the MIDI format is around, which tells you when notes are played, what notes are played in a song, and there are many songs available in the MIDI formats. So we used a library to convert it to JSON, and then used JSON to convert it into timed notes, which is basically when you're going to play what notes. And then a game loop sends you the notes. So I said don't use it for games, but I sort of cheated here. Then I'm using a proxy called Traefik, which is very nice because it gives you, let's encrypt SSL certificates without any configuration. And I'm using a Spring Boot backend, which runs on Docker, and an Angular front end, which runs on Docker. And it's all hosted on a single Azure server. It's not very horizontally scalable because you would have to time sync between the servers. So I wasn't sure how many people were going to show up, and I figured maybe I'd run out of space. But I've tested it before 100 people before, and that worked. So I'm glad it worked today. Lastly, I would like to ask you, please rate my talk in the JFile app. And if you have any questions, feel free to ask them now or later on my email in the bottom. Thank you for your attention.